Hello, everybody. Welcome back to Bayesian statistics. I realized that after last lecture, we are a little bit ahead of the game, which is fine. I charged ahead because I was excited to show you guys the full posterior distribution that you get with 3 parameters. It was a longer lecture. I still fit, well within our 75-minute typical period. But I think looking at the schedule, I figured when I made the schedule that particular lecture was going to take me something like 2. Long story short, I foresee shorter lectures this week. But I really would encourage you guys to go back and, if you have not done so, rewatch the last 2 lectures. Those are pretty pivotal in where we are right now in the class. The other bit of news is homework assignment will be posted this week. I foresee middle of the week posting, and I'm thinking late next week is when it will be due. So you will have at least 7 days, at least full week to do the homework assignment. Last bit of announcement, I'm grading your activities, and those are, as I'm grading them, the grades are going to be uploaded. Please check them out. If you have any questions, please come to my office hours. Office hours attendance has been spotty, I'd say. So please don't fall behind. So big takeaways, we're a little bit ahead. So I'm gonna slow it down a little bit, not have as long of lectures this week. If you are behind, please do rewatch the last 2 lectures. Those last 2 lectures are pretty key to where we are. And watch out for graded activity and the homework assignment being posted later this week. Okay, so let's just briefly 50,000-foot view of where we are in the course. Right now, we're working with what is called grid approximation. So our posterior looks like this. Our likelihood times the prior. It actually doesn't matter if these are vectors as well. This formula does not change. The grid approximation approach says that we're going to use raw computing. And somebody who's made precisely the comment that Bayesian statistics became popular only because of the proliferation of cheap computing power. Now we all have what in the 90s would be considered a scientific, quality scientific workstation, probably have that much computing power on our phones, let alone our laptops. So by using grid approximation, we define a fine grid for each parameter. And we evaluate the full posterior, or the posterior, at every point in the grid. So this really is a teaching tool, because that allows you to literally, programmatically, touch every single point in your grid. You need to define a fine enough grid so that you can claim you actually have the full posterior in sight. So what we have done is we have estimated our posterior for a skew normal distribution. About 1 million points, 1 million grid points. And we're just going to say that is my full, true posterior. But 1 million points is a lot to even plot anything or do anything with it. From this full, true posterior, I took a sample of 50,000 parameter values And that provides a look at the posterior. I can do better than that. That provides an estimate of the full posterior. So that's important because a lot of the time, we don't see the full posterior. A lot of the time, many times, we don't have the full posterior. But we do have the sample of some number of samples from the posterior. So I'm going to repeat that, that's key. A lot of the times we will not be able to completely derive and work with the full posterior, the full true posterior distribution. But in the future, we will be working with some large sample of values from that posterior. So this early in the class, I'm trying to introduce this concept of approximating the full posterior using a sample of values from it. With 3 parameters, we have 1, 2, 3 parameters. Our posterior is 4-dimensional. It's a cloud. It is denser here in the middle, and you can see that it is completely diffuse in a lot of this space. However, mind you, it was still evaluated there. So this is a lot of wasted computational resources all through here. A lot of wasted computational resources. Wouldn't it be great if we had a way of only computing the posterior where it was most likely? Wouldn't it be great if I didn't have to waste my time computing the posterior where it was almost literally impossible? So when we move into Markov chain Monte Carlo, we will see that Markov chain Monte Carlo targets the dense portion. So in 3 dimensions, the dense portion is here in the middle where you think of like a dense cloud or a dense fluid of some sort, maybe an ice cube, right? The ice cube is less dense than water. I messed that up. So MCMC will produce more samples from the dense portion of the posterior than the less dense portion of the posterior. And MCMC will not produce almost any samples from this space that is not occupied by the posterior at all. The way we've approached this so far, grid approximation, we computed it at 1 million grid points, regardless of whether or not the posterior distribution was even possible at that particular combination of grid points, right? Because we're not seeing any posterior out here, right? Posterior probability is essentially equal to 0. Given the data I've observed, that particular combination of points is virtually, parameter values, is virtually impossible. So where we headed in this class, a little bit faster than the book, by the way. The book introduces Markov chain Monte Carlo or MCMC later. I'm trying to introduce it sooner. So I'm trying to give you guys a preview of where we're going. MCMC is an algorithm that helps us target the most dense portion of the posterior without having to compute it at everywhere first. We did it backwards. We computed it everywhere first, and then I sampled with replacement. Sorry, let me flip to R. I first computed it everywhere, and then I sampled with replacement 50,000 times so that a point where the posterior probability was low didn't make it into my sample, and the points where the posterior probability was high did. If I just run this summary of this posterior object, you will see these are actually teeny tiny numbers, but they are as large as, this is 0.01. There are 1 million points there. So if every point was equally likely, right, then there would be no variability at all there. But not every point, and these points are a combination of our 3 parameters. Not every combination of our 3 parameters is equally likely. Some have about a 1% chance of happening. Okay, and that is why, again to repeat, computing outside of this rough cloud-like shape is wasting electricity. It's wasting time, it's wasting computational resources. Okay, so what I did get is a random sample of points from the posterior, 50,000 points, where the probability of making it into the sample is equal to the posterior. That's why it's important that this posterior was a real distribution, because we want these posterior values to be real probabilities. And now I can just use them to these values in my sample to get posterior estimates. So we are here in the notes. These are my Bayesian estimates. Bayesian estimates. Now, unlike frequentist estimates, it's hard to pinpoint a single value as a Bayesian estimate, because what we actually get is a distribution of location parameters, a distribution of scale parameters, and a distribution of shape parameters. I can graph them the same using a histogram, for example. Whoops. All right, there is my posterior distribution of the location parameter averaged over the other 2 parameters. So it's a full distribution. I can pick off any number from there and that will give me something. Now, some values are more useful than others. So for example, I personally really like the median as a particularly useful Bayesian estimate, because the posterior median gives us the typical value of the parameter given this data set. Given this data set, the typical value of our location parameter is 1.7. The typical value of our scale parameter omega is 1.1. And the typical value of our skewness parameter shape is negative 3.7. Remember that of these 3, only the shape is easily interpretable. And that gives us a sense of whether our distribution is left skewed or right skewed. The typical value is negative, so we are, not surprisingly, estimating a left skewed skew normal distribution. Sometimes you will see the mean reported, the average value of the parameter given a data set. To me, it is not as interpretable as the typical value, because it's also, remember, the median is also the 50th percentile. So because the median is the 50th percentile, you can also make a probabilistic statement. So you can say that, for example, I'll focus on the shape. I can say that the probability that alpha is greater than negative 3.7 is 50%, or 0.5. Why? Because it's the median. It's the 50th percentile. Also, by the same token, The probability that alpha is less than negative 3.7 is 50%. And the interpretation of the median as the typical value. We're saying this data is fairly left skewed. We have a lot of evidence that these data are left skewed. In fact, and I'm just showing you how you would interpret a posterior distribution. Notice this. Notice what the 75th percentile is. Negative 3.2. So what we can say is the probability that alpha is less than negative 3.2 is 75%. This is strong evidence of left skewness. There's something interesting. The maximum value in this particular distribution is 0.3. That is a positive value. Remember that we obtain a symmetric normal distribution when alpha equals to 0. Is that a particularly likely scenario given the observed data set? No. But how can I quantify it? Well, for one, I can find my quantiles. I can say quantile of my shape, and I'll be looking for the, say, 95th percentile. The 95th percentile is negative 2.4. So I can say that the probability that alpha is less than, less than negative 2.4 is 95%. Right? So only a 5% chance that our skewness parameter is greater than a negative 2.4. I can keep going. What about a 99th percentile? Negative 2. The maximum, mind you, is 0.3, but the 99th percentile is negative 2. This is strong evidence of negative skewness. All right, let's see if I can catch it. 99.99 percentile. We're still not quite there, but I'm getting closer to 0. I'm getting closer to 0. So I am almost certain, nearly 100% chance that these data are actually left skewed. That the process that has generated log seci in these lakes is a left skewed skew normal distribution. Okay. So we, in summary, obtain a full distribution of values for each parameter. That's the power of a Bayesian analysis. We have infinitely more information about our parameters. We can easily pick off the median values, 99th percentile, the middle 50%, right? How would I do the middle 50%? Middle 50%, or the interquartile range, well, from 0.25 to 0.75. There's my middle 50%. 25% chance of being less than negative 0.44, 25% chance of being greater than a negative 3.2. It's like confidence intervals galore, but I get to make probabilistic statements, and that's the key. So this is also as good a time as any to introduce the trace plot. That is a standard Bayesian analysis figure that you will see in almost every single Bayesian paper and output out there. What a trace plot does, they're kind of simple. They plot the sample value versus the sample number. So sample number is on the horizontal axis, and the parameter value is on the y-axis. So you can see that, remember, we've sampled 50,000 times from the full posterior. You know, just a few times I've caught a location value of around 0.8. You know, just a few times. Oh, there's the one time right there where my cursor is, between the 30,000th sample and the 40,000th sample. I got the one positive shape parameter alpha. Right there. There is my maximum right there. I can see it on my trace plot. So with these trace plots, and this is something I'll be talking about more next lecture, with these trace plots, what we're looking for is a stationary distribution. With trace plots, you're looking for a constant mean, left to right, constant mean, and a constant variance. So you're looking at that, you're basically randomly bouncing around some mean value. And now if I take the mean, I find my posterior mean. If I take the median, I find my posterior median. If I take the standard deviation, I find the posterior standard deviation of each parameter. So I don't want a trace plot that varies, right? So I don't want all right, talking about the trace plots now. I want a trace plot that is stationary. Constant mean, constant standard deviation, same distribution. I don't want this kind of trace plot. Do it in purple because we don't want it. I don't want this kind of trace plot. Because what is the mean, right? This is non-stationary. What is the posterior mean then? And median? We're estimating different means with our samples. But this, we have the same mean and the same standard deviation. So this top, the red trace plot, estimates the same quantity inside the posterior. That's what we're looking for. So on the screen, we have a perfect looking trace plot. And that's the other purpose of this exercise. I wanted to demonstrate what a picture-perfect trace plot would look like because we know for a fact these are random samples from the posterior. In the future, we will hope we are sampling at random from the posterior. But now we know for a fact we have sampled from the posterior because I made it so up here. I have made it so right here. So we will see what these tools look like in the picture-perfect case. Okay, moving on. We've done the code here on line 163 that produces your posterior summaries, and we have interpreted these summaries. But what have we actually said? We have said that our data are left skewed. That is all so far, because C is not the mean and omega is not the standard deviation. In fact, if I go to my trusted Wikipedia page, we use Wikipedia quite a bit, and that's okay. That's okay because it's a resource. It's easier than looking up the original 1985 paper by Dr. Azamini. Because if we see what the mean and variance of a skew normal is, right there is the mean. Let me highlight that. Right there is the mean. You will see the mean depends actually on all three parameters. It's a function of all three parameters. There's C, there's omega, and this delta is basically your skewness parameter alpha over the square root of 1 plus alpha squared. That entire deal times root 2 over pi. Wow. That is the mean. What's the variance? Omega squared times this multiplier that is a function of alpha, right? There's delta right here. Here's the same delta. So, file this under the power of Bayesian. We have a full distribution of C. We have a full distribution of omega. We have a full distribution of alpha. I can now programmatically compute the full distribution of my mean and standard deviation by simply using the samples of C omega, and alpha, combine the mean sample by sample. Combine one sample at a time. And this will give me the distribution of the mean. And the distribution of my standard deviation. I simply combine one C sample at a time with that particular, the first omega sample at a time, with the first alpha sample at a time. And I do that 50,000 times. Thankfully, I have a computer, a very powerful computer. And R likes to think in terms of vectors. So I don't have to even make a loop. I don't even have to make a loop. So this is what this next bit of code does. Notice that line 168 mirrors the formula for the mean, right? Here is the vector of C values. Just to be clear, this is a vector of 50,000 C values, right? This is this vector that I have the trace plot of here on the right. Here is the vector of omega values. Yeah, that's this vector of values. They're not all the same. Here's the trace plot of omega values on the right. And I make, here is my alpha over the square root of 1 plus alpha squared, because I'm trying to mirror this mean right here. I also have root 2 over pi in there. Right? So I'll first make this delta value, and then I plug it into the formula. We combine this mean one sample at a time. This mean now has 50,000 values. I can say length of the mean, 50,000. Very cool. I now have a posterior distribution of the mean. I can now find its median, right? So this right here call it the posterior median, typical value in the posterior of the mean of y. It's the typical value of average log seci given the observed data set. That right there is the typical value of the standard deviation of log seci in the typical data set. And this is the only one that I just grabbed from last time. This is the only one that I don't have to do anything with. I don't have to recombine the other parameters together to look at my skewness parameter. I can make the 95% credible interval. Here I'm using the quantile function to make a credible interval for the mean of my data. I am applying it not to C, but the combination of all three parameters that are produced on line 168. So the interpretation of the credible interval is worth writing out. The 95% credible interval, I think I've defined this before, but it's worth redefining. For the mean. We say that given our data set, there is a 95% chance that the true mean, the population mean, is inside the interval. That is different than a frequentist confidence interval, because I'm not saying anything about resampling data from these lakes. I'm saying that this interval from 0.656 to 0.936, there's a 95% chance that mean log seci is inside that interval. Here is my posterior median in that interval as well. Here on line 173, I reproduce the standard deviation. Notice I take a square root because what Wikipedia gives me is the variance of a skew normal. And I don't need the variance, I need the square root of the variance to get a standard deviation. So that's what I'm doing. I'm taking the square root, and here I'm just mimicking the formula for the variance of a skew normal. And I'm doing so one sample at a time. Right there. I can find its credible interval. So this is the credible interval for the standard deviation of log Secchi, 95% chance of falling between 0.635 and 0.846. I'm reminding you on line 177 that the only parameter I can just take and interpret is this alpha parameter, the shape parameter, the skewness parameter. Here is the 95% credible interval for my skewness parameter. Goes between -6 and -2.2. 95% chance that our log Secchi skewness parameter is in between these two numbers. That excludes 0. That specifically excludes 0. So we can say that our data are significantly left skewed. If you wanted to say that, you could do that because your credible interval, 95% credible interval, has excluded 0 and all the positive values as well. Okay. So I can also look at the trace plots of the mean, the standard deviation, and the skewness parameter. You again see that we have nice stationary distributions. They have a constant mean and a constant standard deviation. There are no patterns in there, a nice stationary distribution. That's what we look for when we look at trace plots. And I'm trying to drive the point home that you can evaluate probabilistic statements about your mean, standard deviation, skewness parameter. So, for example, I can find the probability that my data was actually positively skewed. So probability that my shape parameter is greater than 0. And the way I'm going to do that is first, I'm going to find how many of my 50,000 samples of the shape parameter are below 0. Divide that by 50,000 and subtract from 1. Right? Because I'm looking for the probability of a positive shape parameter. So I'm going to go 1 minus the probability of a negative shape parameter. How many times I observe a negative shape parameter out of 50,000, it is actually 449,999. Only the one time, and you can see it on the screen, this one time that I observe a positive shape parameter. What if for some reason a log Secchi of 0.75 was important? Could I not find the probability of having a mean log Secchi greater than 0.75? I could. I just simply count. How many times do I observe a mean? Remember, I get a distribution of my mean now. This mean is a combination of all 3 parameters. I find how many times out of 50,000 do I observe a mean greater than 0.75? 38,359 out of 50,000. That means the probability of a mean being greater than 0.75, 0.75 is just a number I came up with, is 0.76, so 76.7%. Looks like I was working with a different seed number, and this is off by a couple of decimal points. Okay, this speaks to the power of Bayesian analysis, because in a frequentist world, I would need to use something called the delta method to find intervals for the mean and the standard deviation, because I now have a nonlinear function of the parameters inside there. Delta method works sometimes, doesn't work other times. Delta method is outside the scope of this class, but I hope you can appreciate how easy it is to simply work with the samples that you've obtained to find any quantity out there, no matter how complex, especially when you have good computing at your fingertips. So next time, I'm going to keep going with this example, and we're going to pretend that we have obtained what are called 3 different chains. We have obtained 3 separate samples from this posterior, each one with 5,000 samples. This is going to mirror what we do when we work with Markov chain Monte Carlo. We will start these workers from 3 random locations and let them run for, say, 10,000 iterations. And hopefully those 3 workers converge to the same distribution. And we will be using these tools to assess whether or not our 3 workers, our 3 chains, have converged. So next time, we will see what the picture perfect case of the MCMC looks like, because again, I'll repeat, we know these samples are from the correct target. These samples are from the full posterior distribution that I have evaluated using my graded approximation approach. But that doesn't stop me from pretending I didn't know what posterior I was sampling from. And I can just apply my convergence diagnostics, and we will see again and again, and we will then see what the picture perfect case looks like. Okay, that's the preview for Thursday. Watch out for the homeworks. Watch out for the activities being graded. Thank you guys for your attention. If you are feeling lost, rewatch the videos, please. Thank you guys. I'll see you on Thursday.